Hello, Cosmology from Home. I'm Jamie Sullivan, a grad student at the University of California, Berkeley, and I'm going to talk about some work I've been doing recently on a differential Boltzmann solver, Bolt.jl, with Zach Lee at CETA in Toronto and Marius Milia also here at Berkeley. Okay, so for a brief preview of what I'm going to talk about, first I'll try and motivate why we might want another Boltzmann code, even though there are already some perfectly good Boltzmann codes out there. I will talk a little bit about the goals of Bolt and also how we're going to achieve those goals with the design choices we made. And also I'll show some early results and talk a little bit about what Bolt can do. So the first question you're probably asking is, why do we need another Boltzmann code? Given that current state of the art codes are so deeply integrated into our scientific pipelines, why even bother? Well, I'll give a little bit of context first before talking about that. Boltzmann codes are numerical solvers of the Einstein-Boltzmann system, in particular the linearized system, which describes the evolution of perturbations from the early universe to late times relevant for observations. In particular, describes the evolution of these different species shown in this cartoon here that are of cosmological interest, such as neutrinos, photons, baryons, and the metric. And all of these species are coupled to each other by GR through the metric, but they also have their own interactions between some of them. And this kind of gets at why we need numerical solvers for this system, because the timescale associated with the gravitational evolution is very long, orders of magnitude longer than the short timescale associated with the Thomson scattering between photons and electrons, for example, in the standard picture for the coupling between both photons and baryons. And accurately solving this stiff ODE system requires a numerical solution. And if you work with large-scale structure or the cosmic microwave background, you, I'm sure, are very familiar with Boltzmann codes, since essentially any calculation you do in those arenas requires the use of the Boltzmann code. So to kind of zoom out and motivate from the big picture why we might want a new Boltzmann code, we'll talk a little bit about the state of cosmology today. We are currently in a time of cosmological tension, where for certain cosmological parameters, such as the Hubble constant and S8, a parameter that's describing the matter density and the amplitude of the linear matter power spectrum, different groups and different probes and different analyses are finding discrepant values of these fundamental cosmological parameters. And it may be that these differences will be resolved by unaccounted for systematics, but it might also be that these tensions are physical and can be resolved by model extensions, physical add-ons to the standard ΛCDM model that we use today. And in practice, model extensions that are physical mean adding new parameters for the new components. And it means for a Boltzmann code, editing the source code of the Boltzmann code, because Boltzmann codes are required for pretty much any computation in CMB or LSS. So talking about the first thing first, adding more model parameters is problematic because more parameters means higher dimensional inference. And in all but the most special situations, high dimensional inference is intractable unless you use gradient-based methods. To use gradient-based methods for optimization and sampling of posteriors, you need to constrain cosmological parameters. You need gradients of your model. And if you have something like a Boltzmann code, which isn't analytic, you don't have an analytic gradient in your hand, you need to compute the gradient somehow. One way you can do this is through approximation. You can approximate the model and then get the gradient that way, or approximate the derivative through something like finite difference. Another way you can do this is by using a differentiable model or differentiable simulator. And the Both of these strategies have been embraced recently by different people. There's an example, a few examples of some work on both of these things at the bottom here. But we're going to advocate using a differentiable model, the latter, and in particular using a differentiable Boltzmann code. And this graphic here is just a schematic of Hamiltonian Monte Carlo and efficient high-dimensional sampling algorithm that would work if you had a differentiable model. So now we can finally zoom in on why we want a new Boltzmann code. CAMB and CLASS, the state-of-the-art Boltzmann codes, are, of course, incredible feats of scientific software engineering. A lot of people have worked very hard for many years to bring us a lot of great science with these codes. However, neither of these codes is differentiable, so they're susceptible to these issues of high-dimensional inference if we're considering model extensions. And navigating the source code is a time commitment for these codes. These codes are well designed and usually pretty clear, but we think that there is a way to reduce the amount of time spent going through the source of these codes. And this kind of brings us to Bolt, which is our answer to these two problems. Bolt has two main goals of being differentiable, having gradients available to you, and in particular, exact gradients, which I'll talk a little bit more about in a bit. And also enabling rapid physics prototyping is the other goal for Bolt. We want you to be able to take a model or an idea and go into the source code and have as short amount of time as possible between equation to source code to a plot. And this is the second core idea behind Bolt. And the way the choices we made to try and reach these goals are to use Julia and the automatic differentiation tools in Julia to achieve differentiability, and then taking a spirit of minimizing approximations in order to enable rapid physics prototyping. So I'll talk about each of these things for a little bit. First, we'll talk about Julia. So Julia is a general purpose programming language that promises to have kind of the speed of these heavy duty languages like C and Fortran, but to have the ease of use of something that's closer to Python. In this sense, it kind of tries to solve the two language problem. And you can think about this as if you have a model and you want to try it out, you prototype it in Python. But if you want to get some performance, you have to actually go to C and Fortran and rewrite the code that you already wrote in Python. And the idea of Julia is to kind of get around this by having the best of both worlds. And you can kind of see the reality of the situation of the two language problem in the two main Boltzmann codes today. In CAMB and CLASS, when I interact with it, and I think when a lot of people interact with it in Cosmology, you are using the Python wrapper for these codes, but really underneath the majority of the code is in C and Fortran. Whereas for Bolt, we have the code 100% in Julia. So aside from being kind of having an aesthetic benefit and an organizational benefit, it has a benefit for the user because there's less layers of code to dig through to modify the thing you want to modify if you wanted to add something or to read something. So that's one advantage of Julia. Another advantage of Julia is multiple dispatch. Multiple dispatch is the idea that functions know what to do based on the type of their arguments. And while this seems kind of like a small detail, it reduces the amount of code you need to rewrite if you don't have to define like a long list of functions that are only different in the types of the arguments they take. And also, I'll come back to it, but it's important for the automatic differentiation in Julia, which is the way that we get the gradients for the simulator. And finally, Julia, even though it's a very young language or a pretty young language, it has a rich suite of ODE solvers and automatic differentiation libraries in the SciML ecosystem. The ODE solvers actually are often outperforming the state of the art in Fortran and C, making good on this promise of performance. And there are a lot of choices of automatic differentiation libraries in Julia. One final point I'll make about Julia is that Julia has pretty readable code, in my opinion. On the left, we have some code from Bolt, and on the right, some code from CLASS. And both of these compute the evolution equations for massless neutrinos. And to be totally fair in this comparison, CLASS has 3 lines where they're computing a non-standard contribution. But I think the overall point that, at least for me, I think that the code on the left is much more readable. And if I had to interact with some code or change it, I would choose to work with the code that looks more like an equation on the left here. I think that point that still holds. So yeah, the point of having good readability is such that the user, can go in and modify the code more easily. Okay, and then the last thing about Julia is that Julia has a lot of automatic differentiation tools, and the tools are pretty mature. So now I'll finally say something about what automatic differentiation is. It's how we get the gradients with respect to the cosmological parameters through the simulator. And automatic differentiation is very easy in Julia. It's for here, you have x squared, the function that takes x to x squared. It computes the exact derivative in one line using the Julia automatic, one of the Julia automatic differentiation libraries. This is exact. There's no floating point error. And the way it's doing this is basically by using a chain rule for code. That's what automatic differentiation is. There are 2 versions of automatic differentiation: forward mode and reverse mode. You might be familiar with reverse mode from neural network parameter optimization. When you train a neural network using stochastic gradient descent, it gets the gradients for stochastic gradient descent using backpropagation, which is reverse mode automatic differentiation. In Bolt, we use forward mode automatic differentiation, and that's kind of illustrated here in this graphic. You're basically computing a directional derivative, and as you're going along, you're computing these products, which allow you to have the gradient at the end. I won't get into details here, but the forward mode automatic differentiation is equivalent to something called dual number arithmetic. Basically, this is where multiple dispatch in Julia comes in. You're taking a new type, a dual number, and then just pushing it through all of your code. And this ends up giving you the derivative using forward mode automatic differentiation. And you don't have to rewrite any code to do this. It works for general, extremely general class of functions in Julia due to the design principles of the language. And I'll make the point that we don't have to use forward mode differentiation in Julia. It's just what we're using right now, and we're looking at exploring that in the future. Using reverse mode, that is. One other thing is that all of the ODE solvers in Julia, because of this design principle, you can compute derivatives through them. So that's how we're able to get the derivatives in Bolt. And in fact, actually, the automatic differentiation gives us very high quality Jacobians, which are important for stiff ODE solves, such as those necessary for solving the Einstein-Boltzmann system. All right, the second point to make here is that we aspire to be as close to approximation free as possible in Bolt. And this is a conscious choice. We're trying to minimize the use of approximations in Bolt, even though these approximations can speed up the code. We don't have any tight coupling approximation, ultra-relativistic fluid approximation, or mass neutrino fluid approximations, for example. And the point of this is that if you come up with something new and want to implement it in the code, it should be as close as possible to just working. You shouldn't have to rederive a new TCA and add a whole bunch more functions to your code just to try out something new. Okay, so now I'll talk a little bit about some early results and what Bolt can do. So the first thing it can do is compute gradients, which is good because that was kind of the whole point. Here we have exact gradients of the CMB temperature power spectrum and the linear matter power spectrum on the right. On the left, this is CMB derivative, power spectrum derivative with respect to omega b, the baryon over density parameter. On the right, with omega c, the cold dark matter density parameter. And one thing you might be thinking is that, well, if I know that my observables are smooth with respect to these cosmological parameters, why not just use finite difference? And while it is true that for some of the parameters, you can just do that because the functions are very smooth and slowly varying, there's no reason that this should be true in general for extensions or even for massive neutrinos. It's well known that massive neutrinos don't have great finite difference derivatives. And that's illustrated here in this plot. We have the exact derivative in orange from Bolt, and green is a finite difference derivative with a choice of step size. And choosing the step size is something that you have to figure out, and it's just automatic with Bolt. It's right there. So exact derivatives solve this problem of finite differences. And Bolt is agreeing with CLASS and therefore CAMB at the less than 0.1% level. This is the level at which these codes agree. These codes already agree with each other at this level or better. And now for linear matter power and for perturbations, we're agreeing at the same level. These lines are actually a 0.01% difference here. So this is great. Check on what we're doing to make sure that we're agreeing with the state of the art codes. So the last result I'll show here is that Bolt runs on GPU. So this is the first Boltzmann code that's not only differentiable, but also runs on GPU. These perturbations here for the different species evolving forward in time were, for a particular K mode, were computed on the GPU. There's not a lot of code rewriting you have to do on the GPU because of multiple dispatch, again. And in the right setting, using the GPU can lead to enormous performance gains. And we're interested in exploring this in the future and improving GPU performance. We're also interested in generally looking at reverse mode and eventually making it to the point where we can explore, and you can explore, new physics extensions very quickly. So I'll just leave the summary slide here for a few seconds, and I will just read the words. Bolt is the first differentiable Boltzmann code. It's consistent with CLASS and CAMB at the less than 0.1% level, and it's the first Boltzmann code on GPU. And we want the differentiability for high dimensional inference. And most relevant for you, the lack of approximations and readability are supposed to help you, the cosmologist, to quickly add and test new physics. So thanks for your attention, and I look forward to your questions and discussion.